Hello everyone, my name is Mohit Gupta and I welcome you to my YouTube channel CAM Fundamentals. In today's video, we are going to discuss Graham's law of diffusion or effusion. This is part 3 of the gaseous state. The rest of the parts are given in the description box or in the iCard over here. One more important point, the link of the PDF of this lecture is available in the description box, so go and download from there. So without further delay, let's get started. So first of all, we will discuss about diffusion and effusion. What is diffusion? It is a common phenomena where movement of gaseous molecule occur from higher concentration to a lower concentration. A place where the concentration or the amount of gaseous molecule is very high, they start moving to those places where the concentration or the amount of the gaseous molecule are less. This phenomena is called diffusion, or we can also say that it is the spreading of a gas from one point where the concentration is higher, where the amount is higher, to all the possible space available to it. For example, the aroma of food, the volatile molecules start spreading from the kitchen to the other rooms, and this is called diffusion. Moreover, the fragrance of perfume could be observed if a new guy or a new person wearing it enters to the room. When we light up a cigarette, then the smoke of those cigarettes start moving from the cigarette to the all around the room. So these are the common example of diffusion. Let us understand with the help of a diagram. So in this diagram, I have taken two chambers which are separated by a partition. In the chamber A, I have taken several molecules of A, and in chamber B, I have taken several molecules of B. Now if I remove this partition, what will happen? The molecule of A starts moving from higher concentration, here a lot of molecules of A are available, to the place where the molecules are less. So A starts moving from this container to this one, and similarly B starts moving from this container to the other one. They will move so that they can occupy all the space available to it. It is the property of gas to occupy all the possible space. Okay, so this is called diffusion. Now let's talk about the effusion. So it is the escaping property of gaseous molecule through a small hole under high pressure. What does it mean? If you take a balloon and a lot of gaseous molecule are present in it. Now if you rupture the balloon with the help of a pin, then a small hole will be created and all the gas will release out of that hole. So this is a process called effusion, and effusion is always accompanied by diffusion. For example, leakage in a gas cylinder that occurs due to high pressure. If the pressure is high, the rate of effusion would also be high. If pressure is low, then rate of effusion would also be low. Or if you take a tire which is filled with air, then if it get punctured, all the air inside the tire get released out. Now the important thing is effusion is always accompanied by diffusion. In diffusion, air molecules or the gaseous molecule, they starts moving from higher concentration to the lower concentration. So also in the case of effusion, the same concepts occur. Therefore we always consider effusion and diffusion to be very much similar. The only difference is effusion occur through a small hole, whereas diffusion occur in the free space. For example, if I'll take this chamber in which a lot of B molecules are present, and now if I'll make a puncture here, if I'll make a hole here, in that case, now this B molecule will start moving from this chamber to the outside world. So this process is considered as effusion. Here, one thing important to notice, rate is also considered as velocity. It is the volume of gas diffuses divided by the time taken. So a gas which has higher volume would have higher partial pressure, obviously, and if it has higher pressure, it will move with a higher velocity. So the rate is directly proportional to the velocity of a gas. If a gas is moving with very high velocity, it would definitely have a higher rate of effusion or diffusion. Okay, so let's talk about the Graham's law. In 1831, Thomas Graham has proposed a law while studying a lot of gases. According to him, the rate of diffusion or effusion is inversely proportional to the square root of the density, which means rate is inversely proportional to the under root of density, but at constant temperature, pressure, and volume. The temperature should be constant, the pressure should be constant, and even the volume should be constant. Here, pressure means the partial pressure. So if I'll take two gas 1 and gas 2, then obviously I can compare the rate of diffusion and effusion. For gas 1, R1, it is inversely proportional to the under root of d1. For R2, it would be inversely proportional to 1 by d2. And on dividing them, what I'll get R1 divided by R2 is equals to under root d2 divided by d1. So since the rate is inversely proportional to the density, which means a gas with higher density would have lower rate of effusion, and a gas with lower density would have higher rate of effusion. Now, in some cases, you will find that rate is inversely proportional to the under root of m. This is also a variation of Graham's law. Now, you already know density is equal to mass per unit volume. Now, if you have constant volume, then you can say that density is directly proportional to the mass. Okay, and it is the mass of the gas. What can I write? N into mass of one molecule. So if I have several molecules, so if I'll multiply the mass of one molecule, I'll get the total mass of the gas. Now n is a constant, therefore I can directly say that density is directly proportional to the molecular mass of a gas. So in that case, I can write d1 is directly proportional to m1 for case 1 or gas 1, and under root of d1 is directly proportional to the under root of m1. So I'm taking root on both of these sides. Similarly, for gas 2, I can write under root of d2 is directly proportional to the m2, where m1 and m2 are the molecular mass, obviously. Now on dividing these two equation, what I'll get, under root of m2 divided by under root of m1 is equals to under root of d2 divided by under root of d1. In last case, we have seen from Graham's law, R1 divided by R2 is equals to under root d2 by d1. So since under root d2 by d1 is equals to under root m2 by m1, I can directly write R1 upon R2 is equals to under root of m2 divided by m1. So this is the formula. Here we can see the rate of first gas divided by the rate of second gas is inversely proportional to the molar mass and inversely proportional to the under root of their densities. Now let's take one more case where the volume of two gases are constant, however they take different time to get diffused. In that case, rate is inversely proportional to the time since volume is constant. In that case, what I can write, R1 divided by R2 is equals to T2 divided by T1, because rate is inversely proportional to the time taken for diffusion, and since volume is constant, if I'll divide the two equations, I'll get this formula. And overall I can write this. From these things, we have R1 upon R2 is equals to under root m2 by m1 equal to under root d2 by d1, which is equals to under root t2 by t1. Point to be noted here that t2 and t1 are not in the under roots. Let's take one more example or one more case where the time taken for diffusion is same. Like if I'll take two different gases and if I allow them to diffuse for 5 minutes, then the volume of gas diffused would be different. In that case, the time taken would be same, so rate is directly proportional to the volume, and in that case R1 divided by R2 would be equal to V1 divided by V2. That's very simple. So these are the formula that we have got. So rate is inversely proportional to under root by m, inversely proportional to under root t, inversely proportional to the time, and directly proportional to the volume of the gas diffused. Okay, so let's take one more example where nothing is constant. I have taken the partial pressure different, I have taken temperature different, I have also taken the area of the hole different, volume different, molar mass different. In that case, I can write rate is equals to PA and divided by under root 2 pi RT, where P is the partial pressure of the gas, A is the area of the hole through which effusion is occurring, divided by under root 2 pi RTM, where R is the gas constant, T is temperature, and M is the molar mass. Point to be noted here, if a hole is very large, the gas would take lesser time to get effused. So obviously the rate is directly proportional to the area of the hole. A larger hole would have larger rate of effusion. So if I'll remove 2 pi r, then I can directly write rate is directly proportional to the PA divided by under root of Tm. Let's take an example where I'll take the constant area of the hole along with the constant temperature. In that case, the rate is directly proportional to the P divided by under root m. So I can write R1 divided by R2 is equals to P1 divided by P2 under root M2 divided by M1. And since under root m2 divided by m is equals to under root d2 by d1, I can easily substitute under root m2 divided by under root m1 as under root d2 by d1. So if I have density or if I have pressure, I can easily find out the relative rate of two gases. Now in the second case, if I'll take only A as a constant, in that case P is different, T is different, M is different, density is different. So in that case I can write R1 divided by R2 is equals to P1 divided by P2 under root T2 M2 divided by under root T1 M1. And I can replace M2 divided by M1 by D2 by D1. Let's take one more case where we have two gases having same pressure at different temperature and they are allowed to diffuse. In that case, I'm not supposed to take pressure. The pressure of first equation cancel out by the second equation, and at then I'll be getting R1 divided by R2 is equals to under root T2 M2 divided by under root T1 M1. And obviously I can replace under root M2 by M1 by D2 by D1. So these are the few formulas. They are very simple. You just need to remember the formula of rate, which is equals to rate is equals to P into A, where P is the pressure, A is the area of the hole, divided by under root 2 pi R T M, where R is the gas constant, T is the temperature, and under root M is the molar mass. If you remember that R formula, you can easily find out any of the formula. Okay. So let's talk about the application of Gram's law. Since two gases have different rate of effusion, so obviously on the basis of their effusion or on the basis of their density, we can easily separate two gases. So this process is called atomolysis, where the separation of two gases can be carried out on the basis of their density or the difference in the rate of effusion or diffusion. So application is separation of mixture of gases. Obviously we can separate a mixture of gases. Along with that, we can also separate the isotope of the gases. Since two different gases have different molecular mass, and from Avogadro's law we already know if the molecular mass is different, they would have different density. So on the basis of density or molecular mass, we can easily separate these two gases. Next important application is we can easily determine the molar mass of any unknown gas if we allow it to diffuse, and we can compare it with the gas which is already known to us. So the rate of the two gases can be easily determined experimentally. The molar mass of first gas would already be known because it is already a known gas. So we can easily find out the molar mass of the other unknown gas. So the next point is we need to verify it using the kinetic energy. So this is also a common derivation which can easily be asked during exams. For Gram's law, we already know the temperature is constant, the pressure is constant, the volume is constant. So if two gases have same temperature, which means they have equal kinetic energy. And if they have equal kinetic energy, so we can easily write kinetic energy 1 is equals to half m1 v1 square, and kinetic energy of second gas is equals to half m2 v2 square, where m1 is the mass of the first gas, m2 is the mass of second gas, v1 is the velocity of first gas, and v2 is the velocity of second gas. We have already seen the velocity is equal to the rate. So the speed of the gas with which it is getting diffused or it is getting effused is equals to the rate. Okay, so since both are same, the kinetic energy of both the gases are same, I can easily write 1 by 2 m2 v2 square is equals to 1 by 2 m1 v1 square. Half get cancelled out by the half, but I'll get m2 v2 square is equals to m1 v1 square. So I can rearrange, I can write v2 square divided by v1 square is equals to m1 divided by m2. Now if on further rearranging, I can take under root of m1 and m2. So on doing so, I'll get v2 by v1 is equals to under root m1 by m2. Now the important thing is m1 and m2 are the masses of the gas, the total mass of the gas. They are not the molecular mass. So we can write mass is equals to number of moles into the mass of one molecule, and mass of one molecule is molar mass. Since the number of mole of two gases are same, or it's a constant number, we can easily write m1 divided by m2 is equals to capital M divided by capital M2, where capital M is the molar mass. So I can easily write v2 divided by v1 is equals to under root m1 divided by m2, and v2 divided by v1, v is the velocity which is the rate, so I can easily write rate of second gas divided by rate of first gas is equals to under root of m1 divided by under root of m2. So this is the Gram's law which we have verified it using the kinetic energy. So let's do a few numericals. The numericals of this topic is very simple. You just need to remember the formulas and you can easily find it out the correct answer. So let's take first question. 150 ml of an unknown gas. So you have an unknown gas which takes 60 minutes to diffuse from a vessel. Under the similar condition, 100 ml of chlorine gas take the same time to diffuse. So what we have to find out? We have to find out the molecular mass of the unknown gas. So it is the application of Graham's law that we can easily find out the molecular mass of any unknown gas if we compare it with the known gas. The known gas is chlorine gas, Cl2. We know the molar mass of the chlorine, which is 71 gram per mole. So what is given? V1, the volume of the unknown gas is 150 ml. The volume of known gas is 100 ml, which is chlorine gas. The molecular mass of chlorine, which is M2, is 71 grams per mole. The mass of one chlorine atom is 35.5. So if I'll multiply it by 2, I'll get 71 gram per mole. And we have to find out the M1. So we'll using the formula. This is the formula. And since we have volumes, so volume would be there, and we have to find out the molar mass, so this would be there. On doing so, what I'll get, under root M2 divided by M1 is equals to V1 divided by V2. Taking square on both sides, I'll get 71 gram per mole divided by M1 is equals to 150 ml divided by 100 whole square. On dividing 150 by 100, what I'll get, 1.5, and on 1.5 into 1.5 is 2.25. So I'll get 71 gram per mole divided by M1 is equals to 2.25. So M1 would be 71 gram per mole divided by 2.25, and which comes out to be 31.5 gram per mole. Hence the molar mass of this gas is 31.56 gram per mole. Let's do one more question. Here I have taken HCl and NH3, which are introduced in a 1 meter long tube from the opposite end. From the terminals of the tube, one side we have introduced HCl, and from other side we have introduced NH3. And we have to find out at what distance the first molecule of ammonium chloride will form. So NH3 will move from one side, HCl will move from the other side, and at one point they'll meet with each other. And HCl being an acid, NH3 being a base, they will react to form ammonium chloride, which is a salt. So we have to find out at what length ammonium chloride would form. Now in this case, we have two gases, HCl and NH3. The molar mass of HCl is 36.5, 35.5 for chlorine and 1 for hydrogen, and molar mass of NH3 is 17 gram per mole, 14 for nitrogen and 1 for hydrogen. In that case, we can find out that molar mass of NH3 is lesser than molar mass of HCl. The mass of NH3 would be lesser than mass of HCl, which means NH3 would be able to move faster than HCl. Okay, so let's find out. Molecular mass of HCl is 36.5 gram per mole. Molecular mass of NH3 is 17 gram per mole. And these are the formulas. Here we know the molar mass, and we have to find out the relative rate. So we'll use only this part. So R1 divided by R2 is equals to under root M2 divided by R1. Substituting their values, what I'll get, R1 divided by R2 is equals to 0.68. And on multiplying, what I'll get, the rate of HCl. I have taken 1 for HCl. So rate of HCl is equals to 0.68 times of rate of NH3, which means the rate of NH3 is much higher than the rate of HCl. So NH3 will be able to cover more distance in the given period of time. Now, if I assume that NH3 moves 1 centimeter, then HCl is capable enough to move with 0.68 centimeter. Since length of the tube is 1 meter, which is equals to 100 centimeter, therefore the sum of these two distances would have to be equal to 100 centimeter. So if I let that NH3 travels through x centimeter, then HCl will travel to 0.68 into x centimeter. And on adding that, I should get 100 centimeter. So if I'll solve it, 1.68 into x centimeter is equals to 100, and if I'll divide it by 1.68, what I'll get, x is equals to 59.52. So NH3 travels 59.52 centimeter. Hence NH4 will first appear at 59.52 centimeter from ammonium side. So if ammonia is moving, and when it reaches to 59.52 centimeter, NH3 will meet HCl and they will react to form ammonium chloride. And if you have to find out from HCl side, then you have to minus it from 100. Okay, so these are very simple numericals, and the numerical of this topic are extremely simple. You just need to remember these formula. If you know them, you can easily solve any of the question. So this is it for the today's video. If you like the video, then please hit the like button, and if you're a new viewer, then please consider subscribing. You can go through the playlist of this series as well as the last uploaded video. So this is Mohit Gupta signing off. Have a great day.